Okay, hello. My name is Fredrik Ihøi Fastlia, Fred Fast for short. And I'm going to hold a presentation now about the concept of physical. What really is the physical? So, first, overview, theme, and topic. We humans have an everyday understanding of what it means to be physical, for something to be physical. It has the connotations of being matter and bodily. It is often considered something fundamental and unique, that the physical cannot be created by anything else, that it is a core substance. However, this view is contradicted by modern physics. So this presentation will be an exploration of the physical, and we will see that it has two different meanings, and that the meaning used in modern science, the meaning of physical used in physics, has many surprising and counterintuitive aspects. So, let's go through the contents. First, I'll talk about the motivation for why this topic is important. I will give two definitions of the concept of physical, and then I will question the place of matter in physics, testing the commonsensical properties, such as collisions and the taking up of space. Also, extension in space, which philosophers often refer to as bodies being res extensa, and problems with mass, I will talk about that as well, and arrive at a conclusion. So first, motivation. This is a picture of Thomas Nagel, as we will see. And why is it important to understand the physical? Well, for example, in the paper, What Is It Like to Be a Bat, by Thomas Nagel, very famous paper, the term physical is used quite a lot. Specifically, the paper is about physicalism in the philosophy of mind. And Thomas Nagel says, the meaning of physicalism is clear enough. Mental states are states of the body, mental events are physical events. And in fact, Thomas Nagel uses the term physical more than 30 times in his paper. However, in a footnote, he mentions towards the very end of the paper that he has not defined the term physical. And this is, of course, a huge problem, because if you don't have a clear foundation of what you're talking about, then how can you really trust any of the investigations? I mean, there is a danger that it just becomes intuitive hunches without any real substance. If you want to talk about the physical in a meaningful way, you've got to know about the physical. However, Nagel does have some connotations that he attaches to the term physical. He claims that the physical is objective, and by this he means not having a P of V aspect, not being about points of view. However, this is a huge problem because science is empirical. It's all about points of view. We might try to abstract away from them, but in the end, the points of view of scientists, the experiences that they have, and how we understand them and how we can predict future experiences is all about, is what empirical science is all about. So, but I'm not just going to scold a philosopher like Thomas Nagel, I'm also going to scold physicists. Because this is something that I found from a presentation by a physics teacher. So this teacher claims that physics is the most basic of all sciences. And sure, that's probably accurate. That's the way you can put it. He says that he or she says that physics is the parent of all sciences. Which, you know, it's an analogy, but sure, it works. And then there is a definition of physics there, that physics is the study of the behavior of and the structure of matter and energy and of the interaction between matter and energy. However, this is not a proper definition. And there are several problems here. Most notably, there's a contradiction here. Because if you, on the one hand, claim that physics is the most basic of all the sciences, then you can't just start by assuming that, I mean, being the basis of all empirical sciences, you can't just assume that matter and energy and interactions between matter and energy even exist in the universe. Like, we need first to establish that. The establishment of the existence of matter and energy and interaction between the two is more fundamental than studying these things. Like, we need to know what the pieces are before we can learn the rules about the pieces. And this investigation, what the pieces are, is prior. So the problem is, this definition assumes what is basic, even though that is an empirical question, which we have to investigate first, and it does not account for empiricality. There is nothing here about empiricality. It might be implicitly assumed, but it's not here. So let's go to the two concepts of physical. There is an everyday understanding of physical, meaning bodily, something that is bodily or being matter-like, being a body or being matter, or adhering to these things. But this is inadequate for physics. Because in physics there are things like the curvature of space and electromagnetic oscillations. We see here an electromagnetic field. This is not something that is bodily, but it's very much physical. So let's take a look at the etymology then. The term physics comes from ta physica, which in Greek means the natural things. And of course, physics is an empirical science. And it's about what really, as the most fundamental empirical science, it's about finding fundamental relations and elementary laws that govern what can and will be experienced in our circumstances. So physical, it would be more accurate to say that physical, as the term is used in physics, means something like in accordance with fundamental relations or elementary laws that are empirically verifiable, or part of the fundamental relations or elementary laws that are empirically verifiable. So now let's go to the question of matter. Does matter still have a place in physics? And these two pictures really, in physics conferences, the question of things made of stuff, and in philosophy conferences, is the stuff? This is really what I'm talking about here. Like, all the things that we would ordinarily think of as, stuff, are they really stuff in the commonsensical use of the word? So, is matter still physical? Does matter exist? The commonsensical form of matter exists according to physics. So we'll take a look at a few properties that we would, from a commonsensical understanding, attribute to matter. Well, we know that matter takes up space, and it has a collision box. Two pieces of matter, when you move them together, they collide, they repel each other. And we think of matter as something solid, and matter takes up space. That's the res extensa, which René Descartes made theories about. And of course, there is a concept of mass, which people often connect to matter. But as we will see later, no such matter actually exists. So we will now take a look at these different properties and see whether or not they have a place in physics. And spoiler alert, they don't really have a place in physics. Not in the ordinary understanding that we have of them, at least. So first, let's take a look at collisions and the taking up of space. So the collision box that ordinary matter gets, it gets from electrical repulsion between the electrically charged particles in matter, for example, electrons being very close to each other and repelling each other. Then the Coulomb forces become very strong, so the atoms cannot get any closer to each other due to electrical repulsion. But there is also the exchange force, which has to do with the Pauli exclusion principle. That prevents atoms, particles from being close to each other. So, yeah, the electrical repulsion comes from the electric field that is set up by the charges in atoms, and the Pauli exclusion principle is in many ways a very abstract principle in physics. And the thing is, the electric field is not matter itself. Like, we don't think of a field as being matter-like. You can have several fields on top of each other in a way that matter cannot be on top of each other. So the collision box effect that matter has doesn't come from something that is matter itself, it comes from something very dissimilar to matter. So it's very weird to say that this is matter in this sense. And the Paul exclusion principle is really more, it's not about one little marble pushing another marble away from being in the same space. It's about, the Paul exclusion principle is about quantum numbers, that two different particles, or the same type of particle, but throughout different instances of the same particle, cannot be in the same quantum state at the same time. So it's kind of like a copyright, that when the first particle gets into the state, it excludes all the particles from getting into the same state. It has sort of the copyright for that state, and all the other particles just have to respect that. So it's very much not matter-like, and more like some logical principle that, again, sounds more like a patent or a copyright or something. I was here first, so now you can't be here, even though you could imagine they could both fill up the same space. That's certainly the case for bosons, even though it's not the case for fermions. Yeah, so again, we have the strange thing about atoms, they mostly consist of empty space. So there is no problem conceptually to have the particles close to each other. So they're not solid in that sense, and they don't push each other away in that sense. But there are these things like the electric field and the Paul exclusion principle, which create the repulsion instead. And of course, the fact is that these particles aren't even small marbles. Like, they behave as a cloud, sort of. Like, there is a probability distribution of different places that you can find the electron. And this is very much, again, not matter-like. Like, the electron cloud very much goes against these intuitions that we have about matter. So now let's go to extension in space. Res extensa is, of course, how René Descartes defined material bodies as something that takes up a chunk of space. But of course, at the fundamental level, as far as we're concerned in modern physics, particles are point-like. They don't have an extension in space. The extension in space, as I mentioned, comes largely from electric fields, not the matter that you would think of, the particles themselves. And of course, the fields that are extended, they are not matter-like when they are extended. They don't behave like matter. So the point is, you can have things that are not matter-like, which are also extended in space. So there seems to be there is no one-to-one correlation between being extended in space and being matter. And of course, particles at the atomic level and subatomic level, they have fuzzy boundaries. So it's not like there is a sharp cutoff from where an object stops. There is more of a gradual cutoff, which again goes very much against the res extensa explanation for matter, or understanding of matter. And then we come to the question of whether matter is mass. And Antoine Lavoisier, of course, famously did a lot of experiments on mass, and we will show that, at least in a reenactment of what Lavoisier was doing, the conflation between matter and mass is pretty strong.
Mission to demonstrate that nature is a closed system, that in any transformation, no amount of matter, no mass, is ever lost, and none is gained. Okay.
So we see quite clear conflation. But is this accurate? Is matter actually mass? And we're going to run into some problems there. Because first of all, there are two problems of mass. two concepts of mass. One is inertia, the tendency for things to have resistance to getting accelerated. So if you have like a very heavy shopping cart, you need to apply a lot of force to it in order to get it to move. And there is the concept of gravitational charge, which is also linked to mass. This is what causes gravity to work, causes two bodies to attract each other through gravitation. And first of all, it's not obvious, like from an a priori point of view, it's not obvious that inertia and gravitational charge would be the same concept, or would amount to the same thing. And it's not even obvious that matter, in the commonsensical view, has inertia or gravitational charge. Like in many mythical understandings of how the world works, you don't necessarily think of an object as attracting another object through a field, a gravitational field. That's sort of a foreign idea that came, in the 1600s. So gravitational charge is not intrinsically linked to bodies. You can often think of bodies as needing rest and so on, and perhaps falling to the ground, but it's not obvious that there is a link to gravity here. And the same thing with inertia. You can easily imagine an object which could easily, like even if it exists of what we think of as material, could very easily be accelerated with no effort whatsoever. And of course we have Albert Einstein's famous equation E equals mc squared. Energy is equal to mass times the speed of light squared. And if we divide by the speed of light squared, we get that mass is equal to energy divided by c squared. So if you have an amount of energy, that amount of energy E corresponds to a particular amount of mass m. And you get that mass by dividing the energy by the speed of light squared. So if you increase the thermal energy of a system, for example, you will also increase the mass of the system. And this allows us to get mass from massless particles. So for example, the gluon is a boson, so it's sort of like a ghost-like particle, and it has zero rest mass. Zero. But it has energy, and this energy contributes to the mass of the baryons that make up the nucleons in atoms. And in fact, around 98–99% of the mass of ordinary matter comes from these gluons, or C quarks, which the gluons turn into back and forth. But it's essentially mass from massless particles. And this is an extremely foreign idea to people, that you can have matter from something that is matterless. But you can have mass from something that is massless. You can have mass from a gluon, which is something with energy, something, it's a form of radiation, which or a force particle that has energy, and this energy, even though it's not matter itself, can contribute to the mass of a system. So you have the mass of a system coming from something that is very much not matter. So this does not fit with the commonsensical understanding of matter at all. And you also have mass, even rest mass in ghost-like particles. So you have the W and Z bosons, which do even have rest mass, even though gluons have zero rest mass. The W and the Z bosons have rest mass. So, but these are ghost-like particles. These are also bosons, so they can be on top of each other in a sense that electrons and quarks, the fermions cannot be on top of each other. So these ghost-like particles have, and which also mediate the weak force. These particles, even though they're ghost-like, and they are more of a form of radiation than a form of matter, they still have mass. So something that is matterless still has mass. So there seems to be a very strong disconnect between matter and mass. So, my conclusion is, the physical is being in accordance with, or being part of fundamental, directly or indirectly, observable relations or elementary laws. This is what it means for something to be physical. And a conclusion that we have from the investigations we have made is that commonsensical matter does not exist. When we take a look at what is actually going on in the physics, the matter as we understand it does not exist. What we get instead is other principles, which has more to do with logical structures, mathematical structures, seem to cause something that is similar to commonsensical matter to emerge. But it does not actually exist, only something sort of similar, only something like something that functions in a similar way emerges from other principles. So we need to get rid of the fixation on matter. Like, physics is not about matter. It is not the study of the physical in the sense of the bodily. It has so much more. Physics is about empirically observing things and finding fundamental relations and elementary laws in the circumstances that we can observe empirically. But this gives us optimism with regards to scope in physics, because if it's no longer about a body, if it's about more abstract things like fields, electric fields, and other forms of fields and curvature of space and these things, then we can go beyond a lot of things we ordinarily think of as bodily and still investigate them empirically. And there's still physics. And this allows for human perceptions in particular to be part of physics. And again, this allows for objectives, the science of objectives, to be a part of physics. In fact, it would be the most fundamental part. So, thank you for listening. This has been my presentation about the physical. My name is Fredrik Ihøi Fastlia, and thank you for watching.